Good afternoon, morning, evening, wherever you are. Hello, everyone. Thank you for joining us. My name is Taylor Knight. I am the technical lead with DSIAC, the Defense Systems Information Analysis Center. I am your host today. We are very excited to have Dr. Glenn Dane with us today. He's going to talk about the National Science Foundation's HAMMER Engineering Research Center, give an overview, talk about all the great things they're doing with metals. But before we get started, I wanted to go over a few housekeeping notes. So as you saw in our introduction video, DSIAC offers a variety of services to the defense community, one of them being our free research service, which are called technical inquiries or TIs. You can submit any science and technical question to our analysts and engineers, and we will research it for about 4 free hours. And it will give you a jumpstart on your research. We can answer broad questions about what's going on in a certain topic area down to the very niche questions. So you can submit at our website. I'll put that in the chat. If you have any pressing needs, you can let us know and we're happy to help. Today's slides, so back to our webinar, today's slides, they can be downloaded from the webinar's website. If you haven't had a chance to grab them, I'll also throw that link in the chat. It'll be in a PDF form. There are multiple videos that Dr. Dane has included. You won't be able to see them on the PDF of the slides, but the slides otherwise are there for your viewing. If you experience any technical difficulties during today's presentation, today's webinar is being recorded and will be available on DSIAC's YouTube video in a few days' time. So you'll be able to view that link at the webinar's website, which again, I'll throw in the chat. Finally, if at any time during the webinar you have a question, please try to use the Q&A section instead of the general chat. It just makes it more focused and easier to track. You can find the Q&A in the very bottom right corner of WebEx. There is an ellipses, so once you click on the ellipses, it'll pop up and say Q&A. You can enter it there. If it gets thrown in the chat, I'll be monitoring as well, and I can kind of throw them in the Q&A as needed. Once Dr. Dane finishes his presentation, we'll then have remaining time to answer questions. So with that, I'm going to introduce Dr. Dane. If you want to go ahead and start getting your slides pulled up, I'll read your bio introduction and then we'll get started. Dr. Glenn Dane is the Mars G. Fontana Professor of Metallurgical Engineering at The Ohio State University. He is also the director of the NSF HAMMER-ERC, where he researches manufacturing process innovation in impulse-based processes for joining, shaping, and cutting materials. He was involved in establishing the LIFT Manufacturing USA Institute and Ohio State Center for Design and Manufacturing Excellence and the Ohio Manufacturing Institute. Dr. Dane holds a BS from Northwestern University and a PhD in Materials Science and Engineering from Stanford University. And with that, I'm going to hand the mic over to Dr. Dane.
Okay, thank you so much, Taylor. It's a great pleasure to be here today. Feel free to ask questions as we go, and if you want full slides with movies, I'm very happy to provide them later on. And want to talk a little bit about the center that we have. This will be the primary focus is our center, HAMMER, Hybrid Autonomous Manufacturing, moving from evolution to revolution. It's a National Science Foundation cooperative award. I'll tell you about it. There's a lot of good stuff in here. I urge you to pay attention. We won't waste your time. A lot of very interesting things, and I think there's a lot here we can do with real manufacturing innovation that can serve the warfighter and other needs and really give us much better manufacturing independence in the United States and really support a lot of these foundational economies that we have in terms of metal forming and the like. So, bottom line up front, first of all, I want to say metal forming is an area of huge opportunity. It's how we make both the best stuff, things like aircraft landing gear, forged crafts with wrenches. You always say drop forged on the old school wrenches. Forging does the job of making the very best things. It's also how we make the very best. It's also how we make the most stuff. Things like cans and automobiles. Even if you look at a pen or cell phone, there's a lot of formed metal parts here. There has not been a lot of innovation in the last 50 years, but there is room for a lot of innovation. I hope you see that. And everything that's going on with reshoring to try to make the United States more manufacturing independent is really a great place to drive some of this. We are also here, there's, as you'll see, 5 universities with their logos on the bottom. all great partners of ours in this HAMMER initiative that I'll talk about. We are open to partner. We're interested in developing workforce, innovation, scaling things, and we really believe that this area of manufacturing is ripe for innovation. We want to partner to help shape it. Best way to predict the future is to invent it yourself. That's part of what we want to do. Again, a little bit of applied history. If you look at what's gone on in the United States and my lifetime, so forth, we went from really the world's manufacturing leader to a group that were really good at some level of innovation. We're really good at writing papers, developing ideas, not so good at actually implementing them. And we've developed world-leading industries, machine tools and CNC. This was stuff that was developed between Cincinnati, Chicago, MIT did a lot of this. Microelectronics, born in Silicon Valley, all of the manufacturing, with most of the manufacturing is offshore, with Taiwan taking the lead. Aerospace, we still have a strong export economy in that area, largely because of the protections that have been put in by DoD needs. And nuclear power, we've again largely invented this here in the United States, and most of that manufacturing has really moved offshore. We're no longer a leader. I think we can bring that back. Part of what we have the opportunity, I believe, to do is leapfrog a lot of this and come back with new technology that goes beyond where we are today. That's part of what we want to do. Again, you can't innovate unless you kind of know what the state of the art is. And part of that, you have to go to other countries to see what the state of the art is, see what they're doing in their facilities with their talent, understand the supply chain. Lots of issues with supply chain fragility. And you can't really, if you want to be resilient, you have to be able to make what you need at any given time. Again, this kind of shows up here what's going on with some of the trade deficits. Economists might tell you trade deficits themselves are not a problem, but what is a problem is when manufacturing facilities go offshore and the talents that are associated with it go offshore, your supply chains are less resilient, and you also don't have the talent to innovate. These are some of the things we're interested in. And then DoD has also become very interested in certain particular supply chain vulnerabilities with things like microelectronic chips and batteries. The big surprise a few years ago was castings and forgings were also on that list. That's an area that's near and dear to to my heart. So anyway, I'm an academic. I've been in a university for over 30 years. I try not to make it an ivory tower. We're trying to break down the idea of an ivory tower. I see our role here in the universities as being servant leaders. We want to do things to really help the economy. And in the area of manufacturing, if you look at it, starting here on the right, if you look at additive manufacturing is a thing that everybody knows about. It's taken a lot of interest in academics and elsewhere, but it's a relatively small market. Welding is bigger, casting is bigger, machining, CNC machining is bigger. By far, the biggest of all of these industries is metal forming, and that's the one that I think we really have room for innovation in. And it's how we make big things. It's how we make very good things. And we want to do research and develop in that area. I'll show you a lot of that. We want to educate. We have programs, some of them supported by DoD through the metal program, to educate in the forging area. This comes through IACME. And then we are also partnering with industry, trying to de-risk new technology, provide a base for innovation, and develop the U.S. supply chain. And we're also very interested in developing straight up new business models for all of this. So a lot of this is enabled by a cooperative award we have with the National Science Foundation for what we call HAMMER. I mentioned it before, hybrid autonomous manufacturing, moving from evolution to revolution. It's a partnership between ourselves at The Ohio State University, where I'm the lead, Case Western University, North Carolina Agricultural and Technical State University, Northwestern University, and University of Tennessee, Knoxville. And Knoxville has a number of really impressive things, including Oak Ridge National Lab, where they've got a manufacturing demonstration facility that we're also working with and modeling quite a bit of what we're doing off of. We are about 2.5 years through what should be a 10-year award. We're given about $5 million a year from National Science Foundation that we use to support these programs. Again, we want to partner with you and bring value to DoD stakeholders. And we have foundational components in research, workforce development, developing an innovation ecosystem, trying to found new companies, work with companies, get the IP out of the universities. We're very focused on that, have specialists working on workforce and innovation. And our technical foci are in deformation processing, metal forming, advanced control, Industry 4.0, development of new processes. I'll show you some of that. And then we have a very robust and interesting innovation ecosystem. In part, one of the most interesting things is we've formed a nonprofit that works with our center, and the nonprofit can be used to move much more quickly than a university can. It also is a portal where we can bring the intellectual property from the university to needs in a much more agile way than going through the IP offices directly from the universities. So that's the big idea of what we're doing. Let me move more into the technological focus, the technology focus of what we're doing. This cartoon shows sort of what we're trying to do. If you're trying to make some part, this is like a hip implant. You may use additive manufacturing. I will tell you as a metallurgist that additive manufacturing has challenges typically making some of the very best materials. It also has challenges to go to very big things. These are two primary issues. It's also relatively expensive. What you really want to do is choose the very best tool for the job. This is the idea. You might have a tool rack here. Tools could be used for addition, subtraction, inspection, surface finishing, and so forth. You do this in an environment with robots. You put a lot of sensors around it. And just like a good craftsperson, you try to learn from each experiment and try to get better at this. And this is where artificial intelligence and machine learning comes into all of this. So we want to capture all of that data, use that to improve. So if you have a system like this, this is basically what would be like a tool and die maker's shop that might be sitting somewhere. It's in a contained space with lots of tools that can be used. If you have something like this, you could imagine using this as like at fulfillment centers, forward operating bases, operating rooms, space. These three are all examples of very austere environments, space being maybe the most austere of them. And we also use this for educational platforms. These are the use cases we're interested in. And then we have research programs related to all of these. And we have research thrusts, thrust 1 through 4, related to design, really the tools and integration of those tools, understanding the state of the material as you do deformation. That's your key for quality assurance. Deformation processing, wrought products are almost always better than cast or powder metallurgy components. We lean into that strongly. And then lastly, what we call CIA, control, intelligence, and autonomy. We're trying to do big things with small tools, but tools that are very well controlled. Just like a blacksmith can make very big, complicated things by incremental forming with a high level of control, we believe we can make big things with small, highly controlled components, and we'll show you some of that. The other way we break things up is according to what are called test beds. This is a mandated structure by NSF, but we like it a lot. We like a lot about the way NSF has asked us to set these programs up. And I'll show you examples where we're doing things like point of care manufacturing, numerical forming. We're taking and using deformation with things like additive manufacturing to improve the properties as we develop them. We also have what we call PET fabs, physical exploration and training, factory automation, or artisan boxes. These are the test beds that we are using right now with that. The test beds really support platform technologies, and these are some of the platforms technologies we're working on. So one that's a little bit of a legacy beyond us is Makina Labs. You might have seen some of what they do, but this is incremental sheet forming. This is something we're interested in, not quite core to us, but I'll show you some new things that we're doing. I'm going to show you 2 of 5 platforms that we're working on strongly. One is called the Agility Forge. I'll go through that one in detail. Robotic English wheel. This is a way of doing large, gently shaped sheet components. I won't say very much about this today. Robotic fixation plate bending, I'll go through in some detail. We're taking wire arc additive manufacturing, which can be a low-cost way of making large things by using arc welding deposition, and then forming on top of that. Won't talk too much about that today. Won't talk too much about the American pin bed, but that shows kind of the breadth of the things that we're doing. And again, we can go further from there. We see this going along a path a lot like where you see driving autonomy. You hear about like level 2, level 3 driving. We've riffed off of that to think about levels of manufacturing autonomy. And this sort of, I think, shows where manufacturing is going in my lifetime. You started with no automation, the standard knee mills you might make, and the operator would run the cranks. Then you went into CNC control. Next, you'd go into closed loop control to zero out errors. And we're kind of things are at right now is we often use process simulation with control to try to zero out errors. So model-based process control is a big deal. The things that we're trying to push into that are not common yet are really trying to thread those processes together to give you automated hybrid process execution, where you might go from an addition process to a forming operation, to a machining operation, to a heat treat operation, all pretty much hands off, lights out. That's where we see the future, selecting the right process along the way from multiple processes. And at the highest level, you ask whoever your friend is, Siri, Alexa, to make you something, and it will have a discussion with you, tell you what it would cost, how long it will take. And we notice there are a lot of companies that are along this pathway that we're articulating. Path Robotics here in Columbus, Ohio, for example, is doing autonomy plus welding. There's a lot more that can be done there. So what I want to do in the limited time we have, go through a couple examples of this that show what we mean. And again, there's more to this, but these are good examples. And this is one that we're getting good support. We've just had a program from Blue Forge to do some parts, and then we're also getting some support through Office of Secretary of Defense to develop this concept out more fully. This is something we call the Agility Forge. And this is basically one implementation of a robotic blacksmith. These are some examples of some parts that are made this way. This is taking basically 1.5 inch hex bar. We can bring it down to make small tensile samples. This is all done just by deforming. And we can do things like tie rods. There's a very large universe of parts we can make by this robotic blacksmithing approach. I'll show you how this is done. Why would you want to use robotic blacksmithing? Well, number one, forging makes the best parts, can be faster than machining. Actually, deforming to shape can be faster than machining, doesn't create all of the waste that machining does. So it can be cheaper, got real forgings. This is built on decades of material processing expertise that we know how to access. We can also learn about the material in situ, again, make the process better the next time. And we see that there's demonstrated commercial need here. And the other thing that's really nice is this is basically a mashup of commercial off-the-shelf components with novel software and control algorithms that we're developing, so we can develop this relatively quickly. So let me show you with a movie what this is. This is multi-process, numerically controlled. We believe this is agile, expeditionary, makes real forgings. These are the key parts. It's basically a press with an induction heater, CNC control for location, and then there's something else that keeps you from bringing oversized loads into the unit. So this is an example of how this might be used. You see the CNC motion, putting the part either in a machining head. Again, this is developed for hybrid processes. We might have machining and forging all in the same operation. You can have an induction head here. And then the real cleverness of this is putting this part into a press, and then that press has an automated tool changer in it, and we can go from tools that are used for cogging or poking or bending or cutting or the like, and we can make a large variety of shapes out of it that way. So you see that happening. You see kind of a hole punch operation coming in there. And we've gone beyond just doing this in cartoons. We actually have systems. This is the first such system. You're seeing a part being heated with an induction coil. Then things can be positioned within tools or back into the induction coil for additional heating. And then we can make shapes by this CNC forming operation. And right now this is time lapsed to be faster than, or to speed this up. However, we feel confident that we will be able to go at least this fast as we develop our control algorithms a little bit further. One of the big challenges with all of this is just simple communication protocols between all of the equipment. So now you see a tool change operation, again, which allows you to put multiple tools in that allow you to make a wide variety of shapes. And now when you have hot parts, you can cut them. And you might also imagine having a bar feeder coming in from the back of this so you can make multiple parts, lights out, one after the other. Again, we believe in a much faster manner than could be done even by machining, much less additive manufacturing. So that's a concept. That's not the only way to do things. There's a lot of ways we can do this, but the main things you have here is the acronym we call STARK. You have multiple sensors you could have put in there. At very least, we want to have load stroke measurement on this to understand what the press forces are. We can infer material properties as we go. We need thermal treatment with this. Right now we're using induction coils. There are reasons you might want to use gas forges, pick things up with grippers and the like. You might use plasma torches and the like. Actuators, right now we have a good collaboration with the company Promes that makes a servo-electric actuator that we're using. There's also, you can use hydraulics. You can use power hammers, and these presses can be very large. This naturally scales to things that are way larger than additive manufacturing does easily. Robotics, right now we're using a CNC press. Lots of ways of doing this with other kinds of things, including weld positioners, general purpose robots, gantry presses. And then the heart of it really is in the computation of this, and we're trying to develop software. We will be developing software that's really interoperable with a number of these Stark components. So the thing that's really cool about this is when you're doing a forging operation, every blacksmith knows this, we can control both the shape and the structure of the material. You're seeing this in simulation on the right, and you can see we can understand what the temperature is, the amount of deformation put into the material. That changes things that are near and dear to a metallurgist's heart, like recrystallized volume fraction, average grain size. This is how you get the properties that you want. And by varying the process, it shows average grain size as a function of location. And by varying the process, you can change that and do a lot to really optimize the structure and properties of this. These are degrees of freedom that do not exist in additive manufacturing by using all of this. So that's where we're taking this. And just to show you a little bit more recent video, and by the way, through other support coming through DoD, we're going to be building larger systems like this that we're trying to deploy soon. Our goal is by basically end of calendar year 2026 to have multiple versions of this available for sale and feed needs. So this is how we do this in terms of software. We've got kind of this gaming software that's actually at the heart of this. That allows us to do path planning. And then you see kind of some of the motion involved. This is a standard chuck. Behind that is something we call a compliance device that makes sure that if we push something too hard, it doesn't gobble the CNC press. Again, the press is made by this company Promes. This is a 13-ton press. They've believed in the concept to the point that they've made an investment in a spin-out company. And then Ambro we're using as a company that's making the induction heater. And again, you could see moving to the tools, and this is all in real speed. We can start just touching and then making more aggressive imprints to start making the parts that we are interested in. Again, we can make a whole variety of parts, and we're trying to think about starting with simple things, like there's a lot of forged tie rods that we understand can be logistical hurdles. That's an easy one to start with, and we want to work our way up to getting to the point where we might be doing forged bulkheads and other structural aircraft parts, but we'll probably be starting through ground vehicles as an easier way to do things, easier way to do the quality certifications. So now you see another part that's built into this. This is a laser line scanner. We couple the laser line scanner. You can see the line coming across here. We couple that with rotation, and from that we can build solid models. We can assess periodically where we're at, go in, check the shape, And our goal of this isn't always to make final shapes, but to get something that's close to near net shape that could be finished with forging. So that's the Agility Forge. We're very excited about that. It can be used for many materials, many sizes, many parts. That's in development now. We're working on this literally every day here at Ohio State. We see lots of advantages of this versus machining or casting. One of the big problems you have with machining is you have very often what's called a high buy to fly ratio, meaning you buy this big rectangle of metal when you want this little part inside of it. In aerospace components, buy to fly ratios of 10 to 1 are not uncommon, meaning you're throwing out 90% of the material. And when you've got materials that have low machining rates and high cost, things like Inconels and titanium alloys, we believe that this Agility Forge can be a cost and time saver right off the bat, and we're trying to get there relatively quickly. So that's the first product. Second one, second kind of technology platform I'd like to tell you about. Again, this fits the theme. This is maybe a little less DoD centric, but fits the theme of something we call the BendyBot, or the fixation plate shaper. This is the first version. This is the second version, and this shows how we make bespoke parts by deformation processing. If you're very unlucky and need a fixation plate to repair a fracture or cancer or something in a jaw or anywhere in your body, one of the first things you think about is making this by 3D printing. The way a surgeon does this is by bending a plate in the operating room typically. We have systems that can do this faster and more accurately. And let me show you how that's done. And this is done through our point of care manufacturing. I want to acknowledge Professor David Dean, who's been really leading a lot of this work. You see here, this is what's called virtual surgical planning. This basically has the essential features that these fixation plates have. You can define that, and then that defines the curvature. Each of these screw holes has a normal associated with it. This is a mock-up of what that surgical fixation plate looks like. Typically, these are made out of a titanium alloy. And then once we have that, we can go through and actually execute a bending operation. This is the first prototype version we made of something we call the fixation plate bender. And this, you can see the geometry for the typical fixation plate. And it does exactly what a surgeon would do, but more precisely. Surgeon does this with two specialized pliers. Here you're going through and actually putting yaw, pitch, and roll from one point to the next down this, and in about 90 seconds we can make a full component. And I'm going to skip through just to speed this up a little bit. And then from this you have a CAT scan that shows you what the need is, and you basically get that part out, and that could be used basically anywhere on the body, and there are various thicknesses and so forth, and that can all be dealt with basically in the software. And right now we're doing research to zero out the spring back to make sure that we can really suit needs. This is version 2. You can see a much more robust system that can go to much thicker plates, much better control. We have motors in there that can actually sense the forces and the like. This allows us to start doing something that can be used in the operating room. And we believe that this approach will be very affordable, and it fits within the broad HAMMER mission of really making parts by deformation processing rather than by additive manufacturing or casting or the like. So the process, I want to just take a couple slides on the general process we're following with everything. Basically, we follow the same engineering process of design, build, measure, iterate. And we imagine when we have a need for something, here are some hinges. You might have properties for these hinges. It might be weight and stiffness, or weight and cost, or time to market. And for each of these, we choose some of the best designs based on the properties. We try to make that using our equipment, go back, measure how our prediction compared to our objectives, and we use that, learn, keep running through that process. That's what we want to be doing, and we're going to do that for multiple processes. Again, I mentioned very briefly the English wheel. I don't know if this one is a movie or not. Nope, I think not. If you watch YouTubes or shows on things like automotive restoration, you'll see that the English wheel is something that's very often used to make like fender shapes. A skilled craftsperson could do this relatively rapidly. We're developing robotic systems for doing that. Again, following that general process that we have of design it, execute it, learn from the errors, try to zero those out. And the way we're doing that is largely by having a physical system and then having a virtual system, a digital twin on that. And we basically want those things to eventually correspond. This is work led by Robert Gao at Case Western University and Jane Chow at Northwestern University. And then we go back and revert that to physical. And that's the way we keep closing that loop and keep optimizing the profile. So again, it's an advanced metal forming tool that we believe can be used for things like aircraft skins and the like. And it's different than the single point incremental forming that companies like Makina are working on right now. We're also using physics-informed machine learning and model predictive control to improve this. Again, we've got a physical system. This is a fixation plate bender. We have virtual systems for that. And again, the idea is to have models for this, use the physics of that, plus real observation to close the loop very quickly and give us something that's really optimal and works very well. So that's kind of brief overview of what we're doing with the HAMMER program. I want to talk a little bit about something else I think can be quite revolutionary that we've been working at Ohio State here for close to 30 years in various ways. And this is a completely different way to do welding. And it harkens back to explosive welding, but we figured out how to do explosive welding in a factory or laboratory environment. So from the point of view of basic physics, an ideal dissimilar metal weld, if you had aluminum and steel, for example, or titanium and nickel, doesn't matter what it is, if you can get clean interfaces, the metals will naturally stick to one another. The trick is, how do you get these, how do you keep any oxide from forming? How do you get these surfaces together in intimate contact without any oxide formation? How do you do that? Well, the way you can do that is by impact welding. This has been around for a long time, been used with explosive welding. And basically what happens if this top sheet comes in, collides at a very high speed, you're typically talking about on the order of a kilometer per second, very high speeds, you can form these welds. This is a weld that we formed in the laboratory between copper and titanium. What happens is that impact basically jets off the initial surface and allows intimate contact between almost arbitrary dissimilar metals. And what we're interested in, the material science paradigm, is go from processing to structure to properties. Our process in this case is an explosive-like impact-driven process. We control the metal speed, we control this impact angle. We have a number of ways of doing this. This would be kind of a whole different talk, but we have gotten very good at using capacitor bank discharge, lasers, chemical augmentation, other methods of getting materials moving very, very fast, and we can do some very interesting things with metal forming that way. The important part of this is we can control the impact velocity and collision angle. There's a wide window there where we can get very good dissimilar metal welds. We know how these work very nicely. This shows how this looks in sort of a movie view. You can see the titanium being driven up from the bottom, crashing into the copper, gives you something very similar to what you see in real micrographs. The beauty of having simulations like this is we are able then to measure the temperature, the pressures, what the strains are, what the velocities are of the ejecta, and we can then use this to design systems that are quite effective for making dissimilar metal welds. In the case of copper to titanium, we very often get these beautiful wavy interfaces. We've done a lot of work joining iron and steel. We've also done a lot of work joining aluminum to steel. We've also done a lot of work joining aluminum to aluminum. They don't make as beautiful of interfaces, but again, we can predict it, get beautiful interfaces out of that. So these are some of the pairs that we have joined. Again, aluminum alloys to aluminum, aluminum to steel, dissimilar, similar, doesn't matter so much. One of the great things I think is important about this is we can do this without destroying the metallurgical structure in something like an age-hardened aluminum alloy. So if you hear about 2024 T3, which is the predominant aircraft skin material, that T3 microstructure is important. If you weld it, you end up with sort of a messy microstructure that doesn't have very good properties. That's why you use rivets instead of welds. Welds are really much more effective. But again, this can be applied to a lot of things. This is how you might use this in aerospace joining. We can show you how we can take an inner and an outer, just basically remove a little bit of material off the inner, make sure there's two clean surfaces together, just a little bit of a gap. And then we have this vaporizing foil approach that can drive the flyer into the target, and we can make real welds while maintaining, even having the coating on these things. I'll show you how this is done here. This is something that we've developed here at Ohio State University. This is a vaporizing foil actuator. Basically, it's a electrically driven explosion. This is the flyer on the bottom, the target on the top. The electrically driven explosion is going to drive the flyer into the target, and we end up with a weld that has very good properties associated with it. And this is done with very simple equipment, done in the lab environment. You need to have some kind of an enclosure around it, or it will be quite loud. But we've done this with a lot of very high strength materials, and we've developed some weld schedules that show that we are have properties that are at par or better than rivets, and large savings potentially in weight and complexity by using such a process. And also there's a lot of corrosion issues that might be avoided by using a process like this versus rivets. And the last kind of advantage is we can put these right up at the edge, whereas a rivet you can't quite put at the edge, or it doesn't have anything to grip on. So what we've developed here are systems for doing that, and we've packaged this into a nice small packet that can be used for multiple things. Again, lots of things we can do, lots of unweldable patterns pairs can be put together. And the final example, this is something that we did with Department of Energy. Under their funding, it showed a multi-material engine cradle is possible, where the black material here is steel, the gray material is aluminum, and in this case, I think it's about 40 impact welds have been made that hold this together, and we get very good properties there. And we've built full industrial grade hardware to do all of that. So these long-term problems with dissimilar metal joining are those that we believe we have largely solved over the years, but still need to commercialize further. So just to put a summary on this and leave some time for discussion, I want to kind of talk about some of the things that we've been doing with the HAMMER program. In research and development, we've written a whole bunch of papers, a lot of best paper awards. We have about, the number's higher than 15, but we have multiple, a number of 20 invention disclosures. We're working on multiple engineered systems, many of which I've shown you, some of which I haven't. Two of these are very close to commercialization, including the Agility Forge and the fixation plate shaper. We believe we can make a lot of shapes this way, rivaling in doing better than you can with machining after things are developed. We have an innovation ecosystem with multiple companies involved, and our goal in this is to really help those companies and also develop brand new companies out of this. Also, we're very interested in developing a robust workforce to do everything that is required to take manufacturing to the next level and support this essential economy of making things. Developing manufacturing independence in the United States is more about having facilities and people than just great papers. We're very much into that process, doing a lot of good work with education and outreach. We've partnered with ASM Materials Education Foundation, run Materials Camp for Teachers. We're developing a forging curriculum with the IACME Metal program, and we're very happy with the system that the NSF has set up, the National Science Foundation, through the Engineering Research Centers program, that encourages us to really bring together research, innovation, and education. So with that, I'm going to end and leave some time for discussion. Just put the title slide up again, just as much as anything. So you've got my direct contact information there, should you want to get hold of me. Very happy to tell you about multiple opportunities we have to partner further with DoD or DoD supporting companies or other companies for that matter. So with that, I'll close and thank you for what I assume was rapt attention.
Great. Thank you so much, Glenn. What a wonderful presentation. We have a couple questions that have come in. So if anybody else has questions, now's the time. Throw them in the Q&A or the chat. And I'm going to start reading some out loud. So you have a few related to the Agility Forge platform. The first one is asking, can the Agility Forge platform produce the equivalent of a traditional hammer forged gun barrel? And if so, could it be done fairly rapidly at scale? Has this already been explored?
Yeah, that's a good question. Yeah, I guess I don't know enough about gun barrels right now, but yeah, large, very specialized parts like that maybe not. We're not quite there yet. I think that one is, again, long barrels. You probably need very specialized equipment. However, I will say that where you've got logistic supply chain issues for the components that are ancillary to that, I think we can do that, and that's where we're seeing a lot of interest is in going through kind of the no bid kinds of parts that are often needed for maintenance. Primary gun barrels themselves, I think we still need very large and specialized facilities, but that's something I'd be very happy to think about if, I need to do some research to give you a stronger answer on that though.
Appreciate it. Next one related to the Agility Forge. Are tolerances repeatable after a large number of parts?
Yeah, tolerances are good. Yeah, so we can, part of it depends on having appropriate tools in there. So right now we're dealing with kind of carbon steel tools, but certainly like any we expect to be using tool steel parts before long, a little more expensive, but the tools themselves will not warp. And so we do have two ways of doing that. First of all, we control the displacement on this. We know about the stiffness of the frame and all that. So we believe we can get to pretty good dimensional tolerance, certainly beneath a millimeter. But for anything critical in terms of dimensions, we believe that we typically do final machining. So this is more of a replacement for rough machining with a forging operation than getting high precision. But that said, the other part is most of the time where you've got a CNC machining center, there's the natural cover that comes over that to keep chips in and coolant and all that. We can use that same system to flush the atmosphere and have a controlled atmosphere. So there'll be little to no scale formation on things like steels. So with that, we can get fairly high tolerance directly out of that. So I'm sure we can go quite a bit beneath a millimeter, but that's our target right now, which is a lot like where we're at with hot forging. But with some work, I think we can do things that are like cold forging and the like. Cold forging, a bit of an aside, typically you go with very high pressures and forces with that. We are more on the modest side. We're not trying to make the whole part at once, and the incremental forging allows you to get away most of the time with much lighter tooling, which again makes it more agile, more expeditionary, and that's where we're trying to drive it. So that's the answer in a little more.
Next question. Can or could the Agility Forge be used for critical aircraft parts?
Yeah, we're working that way. There are the issues of certification, quality control, and all of that. We are working at it, but this is absolutely equivalent to a forging. So if you have a forging sequence, we believe we can map that onto the Agility Forge, hitting the same levels of strain, the same temperatures. So basically, we're adapting a forging schedule. It's a much easier problem than additive manufacturing because we have far fewer variables. We're starting with typically wrought material, running it through a forging process, which is well known. And forging does not, if you do it right, we know how to do it right. We do not introduce defects into the material. So additive manufacturing, there's a lot of room for defects. Every machine behaves a little bit differently. So we believe that it requires work and effort, but it's a much easier problem than powder bed fusion, for example.
All right. Also about the agility forge, can the material that's made using this conform to military material specifications, for example, MIL C 24679?
Yeah, we need to do a little more work there, but yeah, I absolutely believe we can get there. I don't know that particular spec very well, but like I say, that's an area and again, we welcome collaboration and work on that, but that's something that in our kind of technical roadmap we see as conformance to military and FAA qualification and specs, all of that as being eventually very important. But we've got to mature the process a little bit more first and show basic demonstration. But these parts are basically forgings in the end, and so the qualification process is not fundamentally difficult.
How do the material properties of impact welding compare to typical welding?
Yeah, good. So with impact welding, we do not have a heat affected zone outside of, there's usually about 50 microns right at the weld joint. But beyond that, you basically see base material properties, no heat affected zone associated with that. When we do tensile or peel testing, when we do it right, we don't always do it right, but in most cases we can get it so it will not fail through the interface, but you'll tear through the base metal, showing that the weld is actually stronger than what's around it. And that's expected because you're getting work hardening in that area. That's a fundamental strengthening mechanism. So we can get very good bonding properties out of that. And then it's really kind of the mechanical design of what's around that. So the fact that there is fundamentally no heat affected zone really simplifies the problem a lot. And the zone that does exist right by the weld interface is actually stronger. The base metal is stronger than what's around it almost always. So simplifies the problem again in some important ways. But again, it's not a terribly mature technology, but I think there's a bit of a leapfrog opportunity with that as well.
Thank you. All right, next question is kind of a two-parter. Do you have any initiatives to address the US's ability or inability to produce complex metal dies and molds to support manufacturing in plastics, composites, etc.?
Yeah, we do. So that one's more done a little bit more through our partners, but there's two approaches to that. So one of our members is Makina Labs out in the LA area. That's one of the areas that they're very interested in is making dies and molds for composites. The other things that we're working on is wire arc additive manufacturing is a very good technique for making molds, but it suffers from a couple of problems. First, when you do the layup, there's a lot of thermal stress involved with that. So as you go from base to something that might be feet up, there's just a little bit of deformation that happens layer by layer. But when you integrate that over feet, the die can warp fairly significantly. So that's partly what we're going to be doing, some deformation processing concurrent with that. So we believe we can take something that's starting to deform and then use a little bit of concurrent hammering. So this is what we call the WAM, wire arc additive manufacturing BAM system, BAM, in order to take that curvature out. The other thing we can do at the same time when you do wire arc additive manufacturing, there's a bit of a rough surface involved, and the machining will often cost as much or more than the basic deposition process. And we believe we can also improve the surface. It still will need final machining, but we think we can really reduce the machining cost with that. So that's another program that we're developing in the coming years.
Thank you. Next question. What TRL would you consider this effort to be?
So the Agility Forge, we haven't done our TRL analysis in a while, but I think we're kind of solidly in the 5-ish kind of ballpark. We're subscale. We're not doing things in a truly full scale. However, it is a manufacturing representative environment. We do this every day. We can come at it and do new materials all of the time. And we have qualified, or we have tested a number of parts that have come off of this. So it still requires scaling. We only have one Agility Forge unit right now. We have plans to build. We have active plans right now to build about 4 more. A couple different geometries and sizes, but I think it can mature very fast. And the reason that I'm really optimistic about it is we're largely using it's a cobbling together of commercial off-the-shelf components, and we've got some really good partners in those components, and those have all been battle tested and hardened to some extent. And it's just a matter it's a significant matter, but making software that works through it and then getting through the qualification stages. But again, we're largely following on the coattails of the forging industry to put the same levels of deformation in at the same temperatures. And I, as a metallurgist, can tell you, if you can do that, you'll get the same properties out. So we feel like we're in a very solid position on all of those things.
Wonderful. That's the last question that I see, unless anybody has another one they want to shoot into the chat or the Q&A. We have a few more minutes. Oh, yep, here's another one. Are you planning to include quenching?
Yeah, we are. So we see this as a platform that we can also, I mean, eventually the Agility Forge platform, you see maybe we're going with a lot of this, but we have the ability to do motion control. We have the ability to do addition. We have the ability to do removal. We will have the ability, all in that same area, to also to do heat treatment. So we see that. I'm not sure where that's useful, but in certain environments, to take that and put it in a Connex box, I think you've got kind of a Swiss Army knife sort of capability that can do a lot of things, and a lot of things that you'd like to do that you can't do now. For example, deposit a wear-resistant area and then deform that all in, so you get a really integrated homogeneous session, really integrated homogeneous part, and then we can do final machining and deformation and all of that. So that's really where we're taking it. That's a bit of a long road, but we believe that the parts are basically there. It's more of a software problem than anything else, and that's becoming relatively easy.
Sure. Yeah, there's one more question. Are there material limitations on the impact welding method you presented here? Impedance mismatch between the dissimilar metals, perhaps?
Yeah, good questions. Yeah, no, there's a lot we do understand and a lot we don't understand there. But everything we've been challenged with so far, with the exception of some nasty coatings, if you get really thick ceramic or organic coatings on things, like we need to remove our organic coatings. They will volatilize on the impact and all of that. However, if you have basically metal to metal, we haven't failed yet with one trick that we will sometimes use, and that's to use an interlayer that could be a third body that's in there. And that sometimes is used. We're not always sure entirely how it works, but it seems like sometimes there's a narrow window there where you get melting before you get bonding, and by inserting a layer in there, it manages the energy, and we've been able to join dozens of combinations of metals. So there are important issues, but not always. So far, we've been able to beat them all. Not to say we always will. And we don't understand everything, and we've done a lot of modeling on things, but yeah.
Yes. Okay, with that, I'm going to have that be our last question. We're just about at the hour mark. I want to thank everyone for joining us, taking time out of your busy schedules. This was a very informative presentation from Dr. Glenn Dane. Glenn, thank you so much for taking time
Thank you
out of your schedule.
Appreciate it, and feel free to reach out to me directly, and happy to continue conversations. So
absolutely. Thank you very much. Everyone have a wonderful day.